Okay, we're going to work through problem 2521 of your text, and it involves a circuit. Let me draw the circuit first, and then we'll read the problem statement. So the circuit looks like this. It consists of a battery, a resistor, and that's it. A battery and a resistor. The resistor R is 20 ohms. The battery is 9 volts. And the circuit is immersed in a magnetic field that's pointing out of the page. So the circuit is in the plane of the page, and the magnetic field is pointing out of the page. And the problem statement reads as follows. The circuit in figure P2521 is a square 20 centimeters on a side, the magnetic field, which is these dots pointing out of the page, the magnetic field increases steadily from 0 Tesla to 0.5 Tesla in 10 milliseconds. So B apparently goes from 0 to 0.5 Tesla in 10 milliseconds, which is 0.01 seconds. That's the magnetic field. Okay, now, let's see what's going on here. I'm sorry. The question then asks, what is the current in the resistor during this time? So we're given this circuit, 20 centimeters on a side. The magnetic field increases from 0 to 0.5 Tesla in 10 milliseconds. And we're asked, what is the current in the resistor during this time? In other words, during the time that the magnetic field is ramping up. Let's just quickly look at what the circuit itself does without the magnetic field. Ultimately, the current that goes in the circuit is going to be driven by the battery, but it also is going to be affected by the EMF induced by this changing magnetic field. We don't know which way that EMF is going to be, which way the induced current would be, and we'll think about that in just a moment. But I want you to notice here that there are two sources that are driving current in this circuit. The battery, and by the way, the battery is driving current in this direction, right? Because there's the positive terminal up on the top. And the current goes through the resistor and comes back to ground. It's also being driven by the induced EMF. The induced EMF, as a result of this changing magnetic field, is going to also generate an induced current around this circuit, and it's going to either add or subtract to that of the battery. We'll find out. Okay, but before we actually consider the field, let's think about the current in the circuit by just the battery alone. We know by Ohm's law that V equals IR, where V here is the V of the battery, and R is the resistor. And, actually, this Ohm's law applies to the resistor itself. The voltage drop across the resistor is equal to that of the battery by the loop rule. And so the voltage drop across the resistor is equal to the current going through it times its resistance value. And we can therefore solve for the current, and that comes out to, we have a 9-volt battery over 20 ohms, and that gives us 0.45 amps. So that's the current that would flow if all we had was the battery. Let's now add the EMF induced by this changing magnetic field. Before we do that, let's determine the direction of the induced current. Remember, Lenz's law tells us that the induced current will be directed in such a way as to produce a magnetic field that opposes the change that produced it. The induced current will produce its own magnetic field. The induced current has a magnetic field that will be directed opposite to the change that produced it. The change that produced it in this problem is that the field pointing out of the page is increasing in time. So it's becoming stronger and stronger in a direction outward from the page. So the induced current is going to produce a magnetic field that points into the page to try and slow down that building magnetic field out of the page. It's going to try and subtract from it. Now, as soon as we know that the magnetic field of the induced current will be into the page, we can use our right hand, point our thumb along the field, and the current that corresponds to that field is clockwise. So the induced current will be clockwise to produce a magnetic field that points into the page to oppose the change that produced it. That's in the same direction as that of the battery. So apparently the battery and the EMF induced by the magnetic field point in have the same sense of circulation. They're both directed clockwise, and so they add to one another. So let's calculate that total EMF. The EMF from the battery is 9 volts. The EMF from the induced is equal to, do you remember what the equation for the induced EMF is? It's Faraday's law. It's delta phi over delta t, where phi is the magnetic flux going through that circuit. The magnetic flux, you'll recall, is B, the magnetic field strength, times the area of the loop. The magnetic field strength that comes through the loop times its area. And the B field is changing in time, the area is constant. So the change in flux, delta phi, which is the numerator in Faraday's law, is going to be delta B times A, because A doesn't change, but B does. So delta phi is going to be equal to delta B times A. Therefore, the induced EMF is apparently going to be delta phi over delta t, which is A times delta B over delta t. This quantity right here, we're told at the beginning, it's up here. B changes from 0 to 0.5 Tesla in 10 milliseconds. So this is going to be the area times delta B over delta t, where delta B is going to be 0.5 Tesla and delta t is going to be 0.01 seconds. What's the area of this loop? The area of the loop, let's just write it over here. A is equal to 20 centimeters times 20 centimeters, which is 400 square centimeters. But we want this in square meters, so that's equal to 400 times 10 to the minus 4 square meters. So we have 400 times 10 to the minus 4 square meters times delta B over delta t, which is 0.5 Tesla in 0.01 seconds. And you can calculate that, and you find that it comes out to 2.0 volts. So apparently the induced EMF is 2 volts, the battery is 9 volts, so E total is going to be 9 volts plus 2 volts is 11 volts, and so the current in the resistor is now going to be 11 volts divided by the resistance 20 ohms, and that's 0.55 amps. So apparently the battery alone drives 0.45 amps, but the contribution from the induced EMF, from the changing magnetic field, adds to the current to make the total 0.55 amps. Notice, if we for some reason saw that the field was decreasing, if we want to consider the case where the field is decreasing in time, the field pointing out of the page is decreasing in time, and therefore the induced current is going to produce a B field that points out of the page to try and support the decreasing field, in which case it would have an opposite sense of circulation. And so in that case we would have the battery and the induced EMF being oppositely directed, and instead of having 9 plus 2 volts equals 11, we would have 9 minus 2 volts equals 7. So there would be 7 volts to drive current around the circuit in that case. Okay, anyway, it looks like the current, the total current in our resistor is 0.55 amps as a result of being driven by not only a 9-volt battery, but an additional 2 volts of induced EMF from the changing magnetic field surrounding it.